Hello, good morning. This lecture introduces the fundamental concepts of symmetrical components and their application in analyzing unbalanced faults in electrical power systems. In practical power networks, the disturbances such as single line to ground, line to line, and double line to ground faults create unbalanced conditions that cannot be easily analyzed using standard balance system techniques. The method of symmetrical components provide a powerful and symmetric systematic approach by decomposing unbalanced three-phase quantities into three balanced sets, positive, negative, and zero sequences. Throughout this lecture, we will explore how these sequence networks are constructed and interconnected to model different types of faults. This framework significantly simplifies the analysis of complex fault conditions and enables accurate calculation of fault currents and voltages, which are essential for system protection, stability assessment, and reliable operation of modern power systems. Okay, this slide introduces the concept of analyzing unbalanced faults in power systems, highlighting the contrast between balance and unbalanced operating conditions. Under normal operation, a power system is ideally balanced, meaning that the three-phase voltages and currents are equal in magnitude and symmetrically displaced by 120 degrees. However, disturbances such as single line to line, and or double line to ground faults disrupt this balance, leading to asymmetrical conditions. So the visual metaphor in this slide emphasizes how even a small disturbance can shift the equilibrium of the system, much like an uneven load affects physical balance. Understanding these unbalanced faults is critical because they are more common than the balance faults and can cause significant stress on equipment, affect system stability, and complicate protection schemes. Therefore, specialized analytical tools such as symmetrical components are used to simplify and accurately study these conditions. Okay, this slide illustrates the concept of locating and modeling an unbalanced fault within a three-phase power system. The system is represented as a single equivalent network where the three phases labeled A, B, and C are shown explicitly. A fault is assumed to occur at a specific point denoted by K, which is referred to as the postulated fault location. This abstraction allows you to focus your analysis on the impact of the fault at that particular point without needing to model the entire system in detail. The diagram also indicates the grounding of the system, which plays a crucial role in determining fault currents and voltages, especially for ground-related faults. By isolating the fault location and representing the system in this simplified manner, it becomes easier to apply analytical techniques such as sequence networks to evaluate the behavior of the system under unbalanced fault conditions and to design appropriate protection schemes. Okay, this slide outline the key assumptions made when analyzing power systems under pre-fault conditions. Before any fault occurs, the system is considered to be perfectly balanced, meaning that all three-phase voltages and currents are equal in magnitude and symmetrically spaced. Under this assumption, um, the symmetrical component networks remain uncoupled and only become interconnected at the fault point. To simplify the analysis, pre-fault load currents are negligible, and which implies that all node voltages are equal to the nominal pre-fault voltage at the fault location. Additionally, several practical factors such as resistances, shunt admittances, rotor silency, and magnetic saturations are ignored to reduce complexity and allow for analytical solutions. While these assumptions are useful for theoretical studies and hand calculations, it is important to note that commercial grade fault analysis software typically include these effects to achieve more accurate and realistic results. Okay, this slide illustrates the pre-fault conditions of a power system and how the network can be analyzed using Thevenin equivalence at a specific node K. On the left, the overall system is represented with three-phase nodes A, B, and C, indicating a balanced operating condition before any disturbance occurs. To simplify fault analysis, the system is viewed from node K and replaced by its Thevenin equivalent circuits as shown in the right-hand side. These equivalents are divided into three symmetrical components: the positive, negative, and zero sequence networks. The positive sequence network includes a voltage source and impedance representing normal operating conditions, while the negative and zero sequence networks consist only of their respective impedances as they are not active under balanced pre-fault conditions. This decomposition is essential because it allows complex unbalanced fault problems to be analyzed more easily by studying each sequence network separately and then combining the result. Okay, this slide explains the analysis of a balanced three-phase fault using the method of symmetrical components. In this case, a fault occurs at node K, and because it is a perfectly balanced fault, the voltages of all three phases at the fault location become zero. That is, VA is equal to VB is equal to VC is equal to zero. The diagram shows that all three-phase conductors are short-circuit together and connected to ground, resulting in equal fault currents IA, IB, and IC following from the system into the fault point. Under such balance conditions, only the positive sequence network is involved in the analysis, while the negative and zero sequence components are zero. This significantly simplifies the problem as the systems can be represented by a single equivalent circuit. Therefore, balanced fault analysis mainly focuses on the positive sequence impedance of the systems to determine the fault current and system behavior during the disturbances. Okay, this slide continues the analysis of balanced three-phase fault at node K using symmetrical components and shows the mathematical formulation behind this. And since the fault is perfectly balanced, the phase voltages at the fault location become zero. So VA is equal to VB is equal to VC is equal to zero. By applying the symmetrical component transformation, the sequence voltages VA0, V1, and V2 are also all equal to zero, confirming that no unbalanced components exist in the system during this type of fault. From the sequence network diagrams on the right-hand side, it is clear that only the positive sequence network contributes to the fault current. The positive sequence current is determined by the Thevenin equivalent as uh, I1 is equal to Vk Thevenin positive sequence divided by Zd Thevenin positive sequence, while the negative and zero sequence currents are both zero. This means that the entire fault analysis reduces to a single equivalent circuit, greatly simplifying the calculation. Therefore, in balanced fault conditions, the system behavior is fully described by the positive sequence network, and the fault current can be directly obtained from the Thevenin voltage and impedance seen at the fault point. All right, this slide explains how a balanced three-phase fault can be analyzed using symmetrical components. In this case, the fault occurs at node K, and due to its balanced nature, it only involves the positive sequence network. The transformation matrix shows how phase currents are related to the sequence components, and since only the positive sequence current I1 exists, the resulting phase currents are equal in magnitude and displaced by 100 degrees as expected in a balanced system. The negative and zero sequence currents are both zero, which significantly simplifies the analysis. The equivalent circuit on the right-hand side illustrates that only the positive sequence impedance contributes to the fault current, leading to the expression of I1 is equal to V1 divided by ZK Thevenin in positive sequence. This confirms an important concept. A balanced fault produces balanced current and symmetrical component, provide a convenient and symmetric systematic way to verify this behavior while reducing the complexity of the system. This slide introduces the analysis of a single line to ground fault at node K, which is one of the most common types of unbalanced faults in power system. Before the fault occurs, all phase currents are zero, indicating normal operating conditions with no fault present. So for simplicity and without losses of generality, the fault is assumed to occur on phase A. As a result, the current in phase A becomes equal to the fault current IF, while the current in phases B and C remains zero. By applying the systematic components transformation, the sequence currents are obtained, showing that the zero, positive, and negative sequence currents are all equal and each carries 1/3 of the fault current. It means I0 is equal to I1 equal to I2 is equal to 1/3 of the fault current. This is a key result highlighting that unlike balanced faults, a single line to ground fault involves all three sequence networks equally. Therefore, in fault analysis, the zero, positive, and negative sequence networks must be connected in series to accurately determine the fault current and system response. Okay, this slide continues the analysis of um, a single line to ground fault at node K by illustrating the equivalent sequence network connections. Since it was previously shown that the zero, positive, and negative sequence currents are equal, each carrying 1/3 of the total fault current, the three sequence networks must be connected in series. The diagram clearly demonstrates this series connection where the same current flows through the positive, negative, and zero sequence impedances. As a result, the total impedance seen by the fault is the sum of the three sequence Thevenin impedances. Using this configuration, the sequence currents can be expressed as the ratio of Thevenin voltage to the total series impedances. Consequently, the fault current is derived as the 3 times the sequence current, leading to the expression IF is equal to 3 uh, times V Thevenin at point K divided by the summation of all of the three impedances. So this result is fundamental in power system fault analysis, as it shows how all three sequence networks contribute to the fault current in unbalanced faults, unlike the balanced case where only the positive sequence network is involved. Okay, this slide illustrates the analysis of a single line to ground fault at node K using the method of symmetrical components. In this type of fault, the three sequence networks, positive, negative, and zero, are connected in series at the fault location. As shown in the diagram, the fault current IF split equally among the three sequence networks, which leads to the relationship I0 is equal to I1 equal to I2 equal to 1/3 of IF. The total fault current is therefore determined by the sum of the sequence impedances seen from node K, uh, resulting in the expression of IF. So you can see here IF by these equations. By applying the inverse symmetrical component transformation, we obtain the phase currents. The results show that only phase A carries current during this fault, while phases B and C have zero current. This confirms the characteristic behavior of a single line to ground fault, where the fault phase conduct the entire current and the system becomes highly unbalanced. Okay, this slide presents a practical example of a single line to ground fault occurring at bus C in a multi-source power system. The network includes multiple generators G1, G2, G3, transformers T1, T2, T3, and transmission lines L1 and L2, all interconnected to supply power across buses A through E. The fault is shown at bus C, where one phase is shorted to ground, creating an unbalanced condition in the system. To analyze this fault, the system is typically converted into its sequence networks, positive, negative, and zero sequences, taking into account the grounding and transformer connections, which significantly affect the zero sequence path. Each component contributes its corresponding sequence impedance, and these networks are then interconnected in series at the fault location, as required for an single line to ground fault. This configuration allows us to compute the fault current at bus C, as well as the resulting currents and voltages throughout the system. The simple highlights how system topology, transformer winding configurations, and grounding play a crucial role in determining the magnitude of the fault current and its distribution across the network. Okay, this slide uh, continues the example of 1010 by showing the sequence network connections and the calculation of the fault current for a single line to ground fault at bus C. Based on the data obtained from the previous example, the positive, negative, and zero sequence Thevenin equivalent impedances at bus C are given as 0.187, uh, J 0.117, and J 0.6 ohm respectively. For a single line to ground fault, these three sequence networks are connected in series and each carries the same current equal to 1/3 of the total fault current. The pre-fault voltage at the bus is assumed to be 1 per unit, which is used as the Thevenin voltage in the positive sequence network. The total impedance seen by the fault is therefore the sum of the three sequence impedances. Substituting these values into the fault current expression, we will have this relationship. Okay, we obtain the fault current as this value, 3.32 with angle of 0 minus 90 degree per unit. So this result indicate that the fault current is purely reactive and lags the voltage by 90 degrees, which is expected since the network is modeled using only inductive reactances. The diagram also reinforces that each sequence current is equal to 1/3 of the total fault current following through their respective sequence networks. Okay, this slide highlight the critical role of grounding in zero sequence networks and its direct impact on fault current flow. Two configurations are compare a system where transformer T1 is delta grounded, delta grounded and delta grounded, and another where T2 is delta ungrounded. In the first case, the presence of the grounded neutral provides a return path for zero sequence currents, allowing them to follow through the network during ground faults. This is reflected in the connected zero sequence circuit, where all elements, including generators, lines, and transformers, participate in the current path. In contrast, in the second configuration, the absence of grounding at T1 effectively blocks the zero sequence current path, creating an open circuit condition. As a result, the zero sequence Thevenin impedance becomes infinite, which forces the fault current IF to zero. This demonstrates that without proper grounding, ground fault currents cannot circulate, emphasizing how transformer connections and grounding strategies fundamentally determine system protection behavior and fault detectability. Okay, this slide raises an important practical question about grounding. Is having zero fault current actually desirable? While it might seem beneficial at first, since no current implies for or no immediate damage, it is in fact a serious problem from a protection standpoint. Protection systems are designed to detect and respond to fault based on the presence of sufficiently large fault currents. If the zero sequence path is interrupted due to improper grounding, the resulting fault current may be too small or even zero, preventing protective relays from detecting the fault. Consequently, the system continues operating under faulted condition without any corrective action. This creates a hidden and dangerous situation where what appears to be normal operation can suddenly lead to severe consequences such as equipment damage or safety hazard when another event occurs. Therefore, proper grounding is essential not only for controlling fault currents but also for ensuring that protection systems can reliably detect and isolate faults. Okay, this slide introduces the analysis of line-to-line fault at node K, focusing on the electrical behavior during a fault between two phases. Here, assumed to be phases B and C. Under pre-fault conditions, all phase currents are zero, indicating a balanced and unbalanced system at the fault location. When the fault occurs, phases B and C becomes directly connected, creating a path for current to circulate between them. As a result, the current in phase A remains zero since it is not involved in the fault. Meanwhile, the currents in phases B and C are equal in magnitude but opposite in direction, such that IB is equal to minus IC is equal to IF. This reflects the fact that the fault current flows from one phase into the other without involving ground. This type of fault does not produce zero sequence components as there is no written pass-through ground and is therefore primarily analyzed using positive and negative sequence networks. Okay, this slide extends the analysis of the line-to-line fault at node K by expressing the phase currents in terms of symmetrical components. From the fault condition, we know that IA is equal to 0 and IB is equal to minus IC is equal to IF. By applying the symmetrical component transformation, the phase currents are decomposed into zero positive and negative sequence components. The results show that the zero sequence current is equal to zero since there is no involvement of ground in a line-to-line fault. More importantly, the positive and negative sequence currents are equal in magnitude but opposite in sign. It means I2 is equal to minus I1. This indicates that only the positive and negative sequence networks are active and are effectively connected in parallel at the fault point. This relationship is fundamental for simplifying fault analysis as it allows the system to be a model using only two sequence networks instead of three, significantly reducing computational complexity while preserving accuracy. Okay, this slide explains the analysis of a line-to-line fault occurring at node K using the method of symmetrical components. In such a fault, there is no zero sequence current, which is why I0 is equal to 0. The positive and negative sequence currents are equal in magnitude but opposite in direction, as shown by I1 is equal to minus I2. These sequence currents are derived using the operator A, where the relationship A minus A power 2 is equal to J squared 3 plays a key role in simplifying the expressions. The equivalent circuit illustrates that only the positive and negative sequence networks are involved and are connected in series through their respective Thevenin impedances. As a result, the fault current is determined by the sum of these impedances and the Thevenin voltage at node K. The final expression shows that the fault current is proportional to the positive sequence current and includes a factor of minus j squared 3, highlighting the phase shift introduced by the fault. This analysis is essential for understanding fault behavior and for designing protection systems in power networks. Okay, this slide present a practical example of a line-to-line fault in a multi-machine power systems and demonstrate how symmetrical component analysis is applied. The system includes multiple generators, transformers, and transmission lines with fault occurring at a specific bus. Based on the result from the previous example, the positive, negative, and zero sequence networks are constructed separately. For an line-to-line fault, only the positive and negative sequence networks are involved, while the zero sequence network is not part of the fault path due to the absence of ground current. The positive sequence network includes the internal voltage source and the equivalent impedance seen from the fault point, whereas the negative sequence network consists only of impedances since there is no source. These two networks are then connected in series at the fault location to determine the fault current. This example highlights how complex power systems can be simplified into sequence networks, enabling systematic and accurate fault analysis essential for protection design and system stability assessment. Okay, this slide continues the analysis of the line-to-line fault by calculating the actual fault current using the previously developed sequence networks. The positive sequence network includes the internal voltage source of 1 per unit and the equivalent impedance seen from the fault point, while the negative sequence network consists only of its corresponding impedance. So since an line-to-line fault involves only positive and negative sequence components, these two networks are connected in series. The uh, the total impedance is therefore the sum of the positive and negative sequence Thevenin impedances, given here as J 0.187 and J 0.117 ohm. Using the relationship between sequence currents and fault current, the expression for the fault current is obtained as this one, this equation. So substituting the numerical values into the formula, this formula, we can find the final result. IF is equal to minus 5.70 with 0 degree per unit. This indicates that the fault current magnitude is significantly influenced by the combined sequence impedances, while the factor minus j squared 3 introduces a phase shift. Overall, this slide demonstrates how theoretical symmetrical component analysis is applied in practice to compute fault currents in a multi-source power system. Okay, this slide presents the analysis of double line to ground fault occurring at node K in a three-phase power system. Before the fault, The system is assumed to be balanced with all phase currents equal to zero. For simplicity and without losses of generality, the fault is considered to occur between phases B and C and ground. Under this condition, the current in phase A is zero, while the ground current is the sum of the currents in phases B and C. Additionally, the voltages of phases B and C collapse to zero due to the fault connection to ground, whereas phase A maintains a non-zero voltage. The diagram visually illustrates the current path and grounding point, highlighting how fault currents flow from the affected phases into the ground. This scenario is essential for understanding unbalanced fault behavior and serves as a basis for applying symmetrical component analysis in power system fault analysis. Okay, this slide continues the analysis of the double line to ground fault at node K by applying symmetrical component transformation to voltages and currents. Since phases B and C are directly connected to ground during the fault, their voltages become zero, which leads to key results. All three sequence voltages, zero, positive, and negative, are equal, and each is one-third of phase A voltage. This is obtained by collecting the transformation matrix relating phase quantities to sequence components. On the current side, because phase A is not involved in the fault, its current is zero. By expressing the phase currents in terms of sequence currents, we derive the important condition that the sum of the sequence current is zero. This relationship is fundamental in constructing the equivalent sequence networks for this type of fault and enables systematic fault analysis using symmetrical components. Okay, I want to close my session here.